Good morning, everyone.
Morning.
How's everyone doing today?
Good.
Great. Okay, there's a few more coming into the waiting room. Let me get everybody in and then we'll get started here. Alrighty, let's go ahead and get going. So we're gonna keep going with our discussion about chapter 3, the electric field. And yesterday we talked about how we find the electric field from collections of point charges, right? We have a functional form for what the electric field looks like coming from a point charge. And we wrote down, right, we practiced using the superposition principle to find the electric field at some point in space coming from multiple point charges. So today we're going to continue with that and try to find the electric field, or practice talking about the electric field coming from what we're going to call continuous charge distributions. What do we mean by that? Well, we know that there's really no such thing as continuous charge distributions because all of the charge on some object is coming from discrete fundamental particles. But if I have a big enough object with enough tiny objects, it looks like there's a smooth, uniform, or continuous charge distribution built up on it, and we can calculate the electric field coming from those type of objects. Okay, so that's the game plan. So let me share my screen. I reconfigured the way I have my iPad set up, so hopefully today it will be stable. I may have just jinxed us. We'll find out. Okay, let's see how this does. Okay, so we're gonna try to understand the electric field coming from sources, right, that are distributed across, right, in some smooth way, right? It's going to be an extension of this superposition principle we saw yesterday. So remember yesterday we practiced with finding electric field by summing components of that total electric field coming from independent pieces of charge, okay? And we went through a problem in some detail where we said anytime we're going to do this, talk about the electric field coming from multiple objects, we want to follow these steps, right? Establish a coordinate system, right? First, draw a diagram, establish a coordinate system, and then what we're going to do is we're going to try to find a way to break objects that we see into small segments of charge. And those small segments of charge that we're going to use are going to be segments of charge that we know how or already have a functional form from the electric field coming from that kind of shape of electric field, right? So right now we have one functional form for the electric field. We know what the electric field looks like coming from a point particle, but we're going to use that to calculate the electric field coming from different types of distributions. And once we calculate, say, the electric field coming from a charged rod or a sheet or a disk, then if we have, say, two disks in space, we can just pull the electric field formula from a disk and calculate, use the superposition principle for the electric field at some point in space from each individual shape to establish the new electric field. Okay, so we're going to slowly build up our toolkit of different known electric fields that we have here. Sorry, I just realized I don't have my chat window open. One second. Okay. All right, great. Okay, so that's going to be the game plan. We're going to find these continuous charge distributions. We're going to find these delta Qs, and then we're going to use the superposition to sum. And we're going to see very frequently that when we make these small segments, we're going to imagine running the size of these small segments to some infinitesimal tiny little pieces. And so to do that summation, right, over some large number, infinite number of tiny pieces, we're going to have to use some integration techniques to do that. And we'll talk about that as we go. Okay. So we're going, right, your book goes through derivations to find electric fields from several interesting geometries. We're going to go through today the derivation of the line charge, okay? And you see the functional form here for an infinite line of charge. But your book also has extensions on the disk, so we'll point out the functional form for the disk and how you extrapolate that to get the infinite plane charge and the sphere of charge. Okay, so some of these I'm going to leave up to your reading. Now I know many of you wrote down in the pre-lecture assignment that setting up these integrals and doing the integral calculus for these different complicated geometries was a little bit unfamiliar. And I recognize that that's the case. And sometimes these are very complicated to set up the formal integrals and solve it in the correct coordinate systems that makes it tractable. So we're going to do that for some key examples, but just know that for most problems that you're going to see on the homework or on the test, it's either going to be something where I try to help you set up that integral, or you're going to be able to use known electric fields, something like the electric field that I show here. Okay. We'll see examples of that as we go along. Okay. So let's get warmed up again just with a quick reminder of electric field and what charges do in an electric field before we start trying to find electric field for more complicated objects. So remember, we have this idea that there's an electric field at some point in space, and if I put a charged particle in that electric field, that it establishes a force acting on that particle. So here's a picture. Let's just say, right, we see some interesting electric field visualized in this picture by those electric field lines, right? These pink lines to the right are showing the direction of the electric field. And remember, when we draw these electric field lines, that we're supposed to understand that the electric field is tangential to this electric field line everywhere in space, and that the magnitude of that electric field is indicated by how closely packed those electric field lines are. So the more electric field lines there are in space, the stronger the electric field, right? So out here I have a weak electric field, and close to this particle I've got an electric field that points tangential to that field line that is stronger. Okay. So which of these positive particles that I place in this field is going to experience a larger acceleration? Let's do that real quickly on the poll. Okay, go ahead. So which particle is going to experience a larger field? Oh, I just gave it away. Okay, good. I'm going to go ahead and end the poll and share the results. Right, almost everybody said A, that the particle that's sitting in the larger electric field, right? I have more field lines packed into a tighter space here, indicating a stronger electric field. If I have a larger electric field and both particles have the same charge, then I have more force acting on it. Okay. So what about this one? Let's do one other warm-up. So what if I have this dipole? I have a positive charge here and a negative charge here. What is the electric field, or sorry, what is the, and imagine that I'm going to put an electron at this point in space. Okay, I'm going to put an electron here. What does the force vector look like on that electron? I want to find the force acting on an electron that's placed at that point. So let's relaunch the poll. Okay, and I'm going to close the poll. We have some, so a lot of people are picking C for the force acting on the electron. There's a fair amount of A, E, right? There's a mix of results here. So let's see what we get. So let's think about the electric field quickly. So if I pick this position, right, I know that a positive particle has the electric field pointing away from it. If I come over here from this negative charge, I know that the electric field on that guy is going to be pointing radially towards that negative charge. Okay. And so when I sum those two vectors together, right, I'm going to get something that looks like E for the electric field pointing down. Okay. But now I'm going to put a negative charge here. So remember, the electron has something like minus a fundamental unit's worth of charge sitting on it. So what does the force look like? The force acting on that electron is going to look like minus a fundamental unit of charge times that electric field. And since I have a minus sign coming from the charge, it means that the force vector is going to point in the opposite direction to the electric field, right? That minus sign is indicating a switch in direction. So my force vector is going to be A. It's going to point upwards here. The electric field is pointing down in this region of space. That means the force from a negative particle placed here points upwards. Okay, great. Let me flip back to this slide here about these electric fields. And I want you to notice that when we go from talking about a point charge, right, that has all of its charge located at one specific location in space, to talking about fields that come from distributions of charges, right? So I am talking about a line of charge that has, right, a rod that has charge distributed evenly over that line of charge, over that space, right, that one-dimensional space, or I'm talking about a two-dimensional area that has charge evenly distributed over this surface. Notice that I have these quantities coming in here, this lambda and this eta term, okay? And these are charge density expressions, okay? So the definition here of lambda is the linear charge density. It tells me how much charge per length I have built up on this rod, right? So if I picked some length L to look at this rod, something like this, and I counted up the charge that was in that region of space, and I took those ratios, I could define this physical quantity called the linear charge density, okay? It has units like coulombs per meter. It tells me how much charge per meter I have built up on this object. A similar idea for this eta, right? This is the surface charge density. This guy, I can imagine defining some surface area A, and it has some charge Q distributed over that surface area, and I could take the ratio, the charge to the surface area, and get something that has units like coulombs per cubic meter, right? How much charge is built up in that two-dimensional area that I've defined there. And the important thing to notice about these quantities lambda is that if I imagine taking, let's look at the rod down here. Let me grab a different colored pen real quick. If I imagine looking at half this length, right, of the rod, L over 2, okay? Well, how much charge is going to be built up that? If I assume that the charge is uniformly distributed over the rod, then if I look at half of that original length that I looked at, then there should be half the amount of charge sitting on that portion of the rod. And that means if I form the charge density, the linear charge density, from that portion of the rod, I would get something that's like Q over 2 divided by L over 2, and the halves cancel out, and look, I get a charge density that matches what I calculated earlier. That's the beauty of these charge densities, is that it's a physical property of the charge distribution that's independent of the particular amount, right? It defines sort of how the charge is distributed, how much charge is packed in any given area. It doesn't depend on the particular segment of the material that I'm looking at. Okay, so let me pause for a second and see what people are saying in the chat. Okay, somebody's telling me there's people in the waiting room. Let's let them in. Okay, so somebody's saying a question that the plane equation doesn't have a 4 pi doesn't have a factor of pi in the denominator. Where does that come from? We'll see that in a second. So your book goes through a derivation. It comes from integrating over some, right, over some surface area. That 4 pi term actually cancels out. Notice that the pi, right, the factor of pi is just some unitless constant. So I'm not changing the units here. The quantity that carries the units is the epsilon naught. So I always have to have that epsilon naught in the denominator to get the right units. But the pi is just some scaling that goes away when I get to these sheets of charge. Okay, we'll see that here as we go along today. Okay. So let's explore those charge density quantities. Let's look at this problem. Let's imagine that I have loaded this rectangular, right, this wire or something that's bent into this sort of square shape. I load it up with 8 nanocoulombs of charge, and imagine it's a conductor, so the charge evenly spreads itself out in a uniform way over this object. What's the linear charge density of this object, right? What's the linear charge density? What is the lambda for the charge on this object? Okay, I'm going to open the polling and give you a minute to calculate. Okay. Okay, I'm see some last answers come in. I'm going to give you 10 more seconds. Okay, let me go ahead and end the poll. Share the results. So C was a popular answer, but we have a good distribution on A as well. So let's go ahead and calculate what this linear charge density has to be. Well, the definition of this thing, lambda, is the charge divided over the length that that charge is distributed. Well, I know that I have 8 nanocoulombs, 8 times 10 to the minus 9 coulombs of charge built up on this shape. What's the length that I'm going to use here? Well, this is a thin wire that's folded over on itself. So I see that I have 1, right? I'm counting the linear distance here. I have 1 centimeter, 2 centimeter, 3 centimeter, 4 centimeter of wire that this charge is distributed over. Okay, so I've got to divide this by 4 times 10 to the minus 2 coulombs. Oops, excuse me, meters. Okay. So that tells me that I should have something, right? If I check the units on this thing, I'm going to have to multiply by 100 in the numerator. So I'm going to get something that's going to be like 800 over 4 nanocoulombs per meter, or something that looks like C, 200 nanocoulombs per meter. Okay. Now I could have calculated this right over, say, 1 centimeter, right? If I just look at this one side of this rectangle, I have 1/4 of the charge over the 1/4 of the distance. I have 2 nanocoulombs of charge over that 1 centimeter of space, and I still get something that's going to be like 200 nanocoulombs per meter. Okay. All right. What about this question? Let's imagine I have a sheet, right, that has length of one side of A and a length of the other side B. And then I'm going to snap it into two pieces below. Okay. The question is, which one of these, how do the etas compare? So I want to calculate the surface charge density on these things. Surface charge density 1. This one's going to have surface charge density 2. This one's going to have surface charge density 3. Okay. Here's what I want you to do. I want you to figure out which one has the largest surface charge density, which one has the smallest. So let's see. Let's come up with a few answers here. Maybe A could say all of the surface charge densities are equal. Okay. Or B, that I have surface charge density 1 is greater than surface charge density 2, is greater than surface charge density 3. Or maybe C, I've got surface charge density 2, or 1 is less than surface charge density 2 is less than surface charge density 3. Or D, I'm going to have something that's like surface charge density 1 is greater than surface charge density 3 is greater than surface charge density 2. Okay. Let's do a quick poll. Which of these is the correct answer here? All right, let me go ahead and end it. We had a lot of people not answer that one. Maybe they're still calculating. And we have split results between A and D. Okay. So let's think about this guy. I have some charge Q distributed uniformly over this object. So I could calculate this surface charge density. It's going to be Q over A, or sorry, Q over the surface area. We know that that surface area is going to be A times B, right? I can just calculate the area for that rectangle to get this surface charge density. What about surface charge density 2 for this guy over here? Well, how am I going to calculate that? Well, I can calculate the surface area. It's going to be 1/3 A times B. How much charge is on this object, right? I took that object 1 and I snapped it, right? I snapped a piece that's 1/3 of its size. How much charge is on that object number 2? Somebody want to put it into the chat or share it? How much charge is on that object? The charge was uniformly distributed over that object 1. And so when I break it off, right, I'm seeing a few thirds. I have 1/3 of the charge on that piece 2. Okay. The thirds cancel out, and look, I end up with an expression that looks identical to eta1. And I could do the same thing for object 3, and I would find that it has the same surface charge density, right? So the point here is that the surface charge density is independent of the amount of, right, the size or what, like the size of the piece of the object that I'm investigating. It's a material property. It's describing some general characteristic of how the charge is distributed over this object. Okay. What about this one? I have a flat circular ring. It's made from a thin sheet of metal, and it's going to carry some amount of charge Q uniformly distributed over its surface. We're going to assume that W is very small compared to the radius, so it's essentially like a line, just like a one-dimensional loop that we have here. What's the surface charge density for this ring? What's the surface charge density going to be? Let me open up the poll. All right, I'm going to give you guys 10 more seconds. Okay, I'm going to stop the poll, share the results. Most popular answer was A, followed by D. Okay, so how are we going to do this? The surface charge density should be the charge, so they just tell us that there's some charge Q built up on this thing, divided by that surface area on this object. Well, what's the surface area going to be? Well, I can see this top object. I could imagine cutting this ring at this place and sort of unfolding it. So I'm going to imagine that this is like a rectangle. It has a width W, and it has some length, right? This side, the circumference, right, is going to be like 2 pi times the radius. And so I know that the area, right, of this thing here, the area is going to be like that width times 2 pi r. Okay. But, okay, so that would require, right, if this is really a physical sheet of charge, remember that the charge is going to distribute itself on the top surface of this object, but the charge is also going to distribute itself on the bottom side of this surface. So there's actually two copies of this surface area. One is the top area of the ring and one is the bottom area of the ring. Now, if this was really just like an infinitely thin sheet of metal where the charges could only live in that two-dimensional plane, then I wouldn't need this factor of 2. And so the answer here is a little ambiguous because they're not exactly clear. So the answer here would be this guy if it's a three-dimensional ring that has some actual thickness, but it would be 2 if this was a flat two-dimensional ring. Okay. So if you want to be really precise, if it's a physical object that has some thickness, that charge can distribute itself on the top and bottom surfaces here. So if it's an actual physical ring, we would probably say B is the case. But if it's thin enough, then I think, then D is a pretty reasonable is a pretty reasonable estimate. Okay. So now we come to a derivation that I want to work through with you in the remainder of time here. Basically, what we want to do is go through and figure out how we derive the equation for the electric field coming from a rod of charge. So here's what we want to do. We want to think about this position in space that's at some height that we're going to call y above some line of charge. So we're going to just imagine this is a thin rod that has some charge Q built up on it. And it has length L, and this position is right in the middle of the rod. And we're going to call that the y direction. So we're defining a coordinate system. This is my y direction, and this is my x direction. Okay. And what we want to do is we want to find what the electric field looks like at this point in space. What is the electric field up here? Okay. Well, how am I going to calculate the electric field there? Here's the general technique. I'm going to take this charge distribution, this line of charge, and I'm going to divide it up into a bunch of tiny pieces here. I'm going to divide it into these little segments, and each one of these little segments carries some fraction of charge with it that we'll call dq, just a tiny amount of charge. And we're going to shrink that charge down to a small enough size that essentially that is going to act like a point charge. Why do we want to do that? Because if this is a point charge, right, then we know what the electric field looks like coming from that point charge. If it's a positive point charge, the electric field out here coming from this particular piece of charge is going to point, right? Imagine we call this like electric, we call this like DE. We call this DE, some little component of electric field coming from that little piece of charge, DQ. It's going to point radially away from that piece of charge. Okay. And we know how to calculate that because essentially it's a point charge, and so we already know the functional form of the electric field from a point charge. It's just going to be 1 over 4 pi epsilon naught, the amount of charge divided by the distance. What is the distance here? The distance is this distance that I have to calculate here. Okay. Well, what is that distance going to be? It's going to be like x squared, whatever my x coordinate is plus y squared, right, square root. That's that distance that I am away from that position on the rod. Okay. And then if I want to find the total electric field, right, so how am I going to find the total electric field acting on this guy? Okay. Well, I'm going to take and I'm going to sum up, right, all these little electric fields coming from a bunch of, right, I'm going to look at every little, right, I'm going to find another DQ over here and then another DQ, and I'm going to scan over this whole ride and find the electric field contribution coming from all these little tiny pieces of charge. So I'm going to integrate, right, the electric field, all these tiny electric field contributions over the whole length of the rod, right? So from, right, I'm going to integrate this over y from one end of the rod to the other. And this electric field, right, we know that I can calculate that. The delta L's are just going to be like dq, right, that amount of charge that I have built up on that thing, divided by the square root of x squared plus y squared times, right, and then I have my 1 over 4 pi epsilon naught. Each little portion of charge is going to contribute that much electric field, right? So that dE I just replaced by that differential expression there, because that's the electric field coming from this delta Q. But we'd like to express, so the problem is, how are we going to do this integral? Because, right, how do I integrate over Q? That's the problem when I have some length of rod. So I need a way to translate that differential expression into something in terms of a spatial coordinate. Okay, and here's how we can do it. We can do that through the linear charge density here. We can calculate the linear charge density for this rod. It's just going to be Q divided by L. Okay, I know the total amount of charge on that rod and I know the total length. So I know this is Q over L. And we can now make this another argument here that if I look at this tiny line segment, right, this tiny segment of charge, well, it has charge dq, and it has length dx, a differential in x, and that has to be equal to the linear charge density, because remember, we've already seen that the linear charge density is independent of the amount of the object that I'm studying. It's a fixed material property. And this is great because now I have a translation here that lets me write down that this thing looks like, right, this thing I can translate and get that dq is equal to lambda dx. So where I have that dq in my integral, I can replace it by lambda dx. So I end up with something that looks like this. The total electric field is going to equal the integral of lambda dx over square root of 4 pi, square root of x squared plus y squared, and then I have my 1 over 4 pi epsilon naught sitting out here. But something is still not quite right. So I could integrate this, right? So this thing would give me, right? What's the problem here? If I did this integral right now, I would have to, right? This is some distance r here, and I'm calculating at a fixed y. So this thing I would only be integrating over the x position, and what I want to find, right, is essentially how I would, right? How I would find just. Right, this thing is, I wrote down the total electric field here. This guy here is giving me, right, something like the total electric field. But I can make things a little bit simpler by noticing something about the symmetry of this problem. So here's what I want to notice. This is a trick. right, to make this integral a little bit easier, that I want to notice that for every charge that I find, delta Q that I find at a negative value of x, I can find a similar small chunk of charge at a positive x value. And why is that interesting? Because this guy is going to be contributing an electric field that points in this direction. And notice then that the y components, or sorry, the x components of the electric field are going to cancel each other out, but the y components are going to add together. So there's this symmetry. Because I'm right in the center of the rod, as I integrate over these charges of the rod, I should see that the x component of the electric field cancels out as I go across this rod. Now that's only because I'm sitting right at the center here. I'm sitting at this point of symmetry. But we're going to use that as a little bit of a trick. So we can see that the total electric field here that I calculate at that point in space is going to be equal to the total electric field pointing just in the y direction. So I only really have to think about what's happening in the y, because I can see just from symmetry that the x component is going to integrate to 0. And if I want just the x component, right, or sorry, if I want just the y component, let me imagine that I have an angle theta here. Well, the y component of this electric field, I can translate that theta up here. Okay. And the y component here is going to be like sine, right, right, remember, sine of theta is going to be like the EY over the total E. Right? And so if I just want EY, it's going to be the total electric field times the sine of that angle. And I can see from this similar triangle that the sine of that angle, right, is going to be, right, I can see that sine is going to be this opposite side, which is y, over the hypotenuse, which is square root of x squared plus y squared. Okay. So that means that this thing, right, I can do this, I can integrate from minus L over 2, that's the furthest extent to x that I want to be in, up to positive L over 2. Okay. Lambda square root of x squared plus y squared. And then I'm going to have another term, right, and then I'm going to multiply this by sine of theta dx. And then I have my physical constants. I can just pull those physical constants out front here. Okay. This sine term, right, we just wrote down is going to be y over square root of x squared plus y squared. Okay. And that's the integral I have to calculate. Okay, that big messy integral here. So let me scrub some of this off here. Sorry, I should find a better way to do this. So let me get rid of this piece here. And we can see that I have something that says the total electric field, right, at that point in space has got to be equal to 1 over 4 pi epsilon naught integral minus L over 2 to L over 2 lambda. Now I have two factors of that, so it's going to look like x squared plus y squared y in the numerator dx, something like this. Okay. Oh, sorry. I'm looking at this. I see one mistake I made. Does anybody see my mistake? Somebody's asking. So sorry. Somebody's asking why is it L over 2 for the integration points? Remember, because I'm cutting the rod, right? I'm basically making my origin here at the center of the rod. So this goes from L over 2 over here to minus L over 2. That's just because I'm setting the origin at the middle here. So I made one mistake here. Up here when I set the total electric field, remember the electric field goes like the charge over R squared. So I should have squared this bit in the numerator here. Okay. So that means this bit should have been squared. Sorry, I missed that one. So let's redo that. And I get something that looks like the total electric field is 1 over 4 pi epsilon naught integral minus L over 2 to L over 2 lambda square root x squared plus y times y over x squared plus y squared dx. Okay, I get this funny integral. But that's fine. This is an integral I can calculate, right? In this particular example, y is a set value. I'm just looking at that specific position over this function, and x extends out. Okay. So, setting these kind of integrals up can be a little tricky, and you saw that I stumbled because I forgot the 1 square. Okay. Now the beauty is though that once we do that once, we're done, right? So the answer here is which is the y component of the electric field. We calculated that. It should look like, which one is it? It's this guy here, d. Lambda dx 4 pi epsilon naught. There's our r squared term, and this is that sine expression that we have sitting there. Okay. Now if I go through and I calculate that integral, right? You could plug it into your calculator or some numerical device. And sorry, I have a few questions. Let me go back. So this big mess. So Aaron is asking, wait, why is it L over 2 for the integration point? So again, we're using minus L over 2 to L over 2 because we set the origin of our coordinate systems at 0 so that I have this symmetric integration. Okay, so that means in this coordinate center system, x equals 0 is at the center of the rod. The rod has total length L, so I'm at positive L over 2 on the right-hand side, negative L over 2 on the left-hand side. And the y, this guy, right? So this piece came from r squared, right? The x squared plus y squared, that's just r squared. So that comes from the point, the electric field form coming from a point charge. And this square root of x squared plus y squared with y in the numerator here, this is equal to sine of theta. Okay. Okay. When you finish doing that integral, you end up with this answer here, that the electric field at this line that bisects a rod of length L, so right in this middle point with some total charge Q, is just equal to 1 over 4 pi epsilon naught, the total charge built up on the rod, divided by L times the square, or divided by R, which is the distance that I am away from the rod, times the square root of R squared plus L over 2 squared. Okay. So, this thing looks like a big mess, and I agree that these integrals, this is probably something totally foreign to you, to go from taking a bunch of little charge differentials, converting them into some spatial differentials using a density function, and then integrating over the path. But the book gives you several examples of that, and the nice thing is that once we calculate it, set up that kind of nasty line integral, that then we have this function for all of time. So now we know that anytime we get a rod with some charge on it, I don't need to go back and do this integral. I can just use this functional form that I calculated. Now, if I change it, if I were to look at a point that's not directly in the center, I've got to go back and do a new calculation. Okay. So somebody is asking though, is lambda supposed to be over r squared? Lambda is supposed to be over r squared. Yeah, so the lambda piece, yeah, I mean, that's where we wrote it. Somewhere we had it here, right? This is the, I mean, maybe I put them in a funny order just because I was writing, right? It's the lambda over r squared, right? This term you see here, lambda over x squared plus y squared. Okay. Again, you can look back in your book. They go through this derivation step by step. So I don't want you guys to, right? If you have questions when you're going through this derivation, I want you guys to at least try to be able to go through this derivation on your own, following along for the book, but really make sure you understand how at least the line charge is derived. Okay? Because if you get that, then I think it's going to be more clear how they derive some of the other charge distributions. So now that I have this functional form for the rod, I could ask a question. What does the electric field look like coming from an infinite line of charge? Okay. And this is what your book likes to, one of the sort of general solutions for an electric field that we want to calculate. So if I run this, right, I imagine that this is going to go on for infinity in this direction and say minus infinity in this direction. I want to imagine that my rod doesn't stop in any position, but just continues on forever. Okay. What do I really mean by that? I mean, I know that I don't ever have some rod of charge that goes off for as long as I can see. But what we're saying essentially is that length L is going to be very, very large compared to the distance that I am away from the rod. Okay. I want to imagine that I'm looking at the electric field really close to the surface of the charged rod, so that if I had my, my nose or my eye, essentially I would never be able to find the end of the rods, that it would just look like it carried off to infinity. Okay. Well, I can calculate this electric field now very quickly just from this functional form that I calculated from the finite rod. Okay. Well, how am I going to do that? Well, I see that L is very, very large compared to R. So here's what I'm going to do. I'm going to pull out from that numerator here, okay? I'm going to pull out L over 2 out of this expression. Okay, so I'm going to factor that out. So I'm going to end up with something. So let me rearrange this. Let me erase this bit here. So I just want to rearrange this expression and rewrite this like this: 1 over 4 pi epsilon naught, and then the charge Q divided by, and now it's going to be R, and then I'm going to have square root of, and now I'm going to pull that L over 2 squared out in front here. So I'm going to end up with something that's like L over 2 squared times R squared divided by L over 2 squared plus 1, something like this. Okay. And then, right, so I just pulled that out. Now this L over 2 squared is under this square root, so I can rewrite this a little bit further. This now looks like 1 over 4 pi epsilon naught Q divided by R, and now I just have L over 2, something like this. And then I have, in here, I've got the square root of R squared over L squared over L over 2. Plus 1. Okay. And so now here's what I want to do. I just saw that I have this limit here, that L is huge compared to R. And so that means that this term here, where I have R over something that's like L, that I can neglect this because this is going to be a very tiny value. Okay, it's going to be a very tiny value. And so now what I see is that this expression, right, and this is where we're going to end for today, I have a thing that's like Q over L. Well, what is that? That's just my lambda. So this looks like lambda over 4 pi epsilon naught. And then I have this factor of 2. So this looks like, right, so this actually is going to become a 2 in the denominator because of that divided by 2. and then I have a R sitting in here. So notice that I get that electric field, right, is equal to lambda times pi epsilon naught over 2r. And if I flip back to the beginning of our lecture notes from today, right, here's the line of charge. This is exactly the expression we got for the electric field coming from an infinite line of charge. Okay, so that's where, and they go through this kind of thinking several times, right? You can take any distribution of charge, break it into small pieces that act like point charges, integrate that at some point in space, and then imagine, if you want to, taking and expanding that object to some infinite size or looking at it under certain distance scales to get the behavior for some infinite distribution. So the infinite plane, you'll be able to see in your book that they essentially calculate the electric field at some point perpendicular to the middle of a disk. And then once they have that electric field, they expand it out to, right, an infinite plane. Okay, I know that was a long lecture with a lot of talk about integrals and derivations, but I really just wanted to go through that setup for you one time in class just to talk through these pieces. So tomorrow what we're going to do is we're going to pick up here, and we're just going to do some final practice with using the derived electric fields from some of these interesting charges to calculate electric fields and do some interesting problems. So we're going to finish off this chapter tomorrow. I apologize for keeping you guys 2 minutes late today. If you have any last questions, I can take those now. Otherwise, you guys are free to go. Thanks so much. Any final questions?
Can you go back to the second problem we had?
This one?
No, at the beginning of class.
This guy?
Yes. Can I see the explanation on that again? Your work?
Oh, my work? Yeah. I mean, it's basically just that it was asking about the force, right? Right, it's asking about the force. So we found the electric field, right? The electric field from the positive charge points in this direction. The electric field from the negative charge points in this direction. So the total electric field points downwards coming from this dipole. And that means the force, right? If I put an electron right at the center of this, right at this position, then the force points against the electric field because there's a minus sign for the charge.
Oh, okay, I get it now. Thank you.
Yep. Loki, you can use K if you'd like to. Yeah, K is just fine. He says, why don't I use that constant K to clean things? Why do I keep writing this 1 over 4 pi epsilon naught? It's out of, yeah, people write K. You're going to see that the epsilon, it's because this epsilon naught thing is the piece that carries units with it. And it's a constant that's going to hang around, and it's going to help us tie the electric field to the magnetic field in later chapters. But for now, you guys can just carry K, and I'll convince you why most physicists forget about K and start writing everything down in terms of epsilon naught when we get to that part in the course. K is more compact for now, though, so if you want to carry K around, that's fine. Okay, any last questions? Okay, thanks everybody. We'll talk to you tomorrow and wrap up this chapter. I'll see you then. All right, bye-bye.
Thank you. Bye.